Thank you. So today I'd like to talk about the new experiment data on the sound velocity of a liquid light ion light element alloys under pressures and temperature using inelastic X-ray scattering spectroscopy. How can I? So consideration of the density and the core. The seismological observation PREM shows the liquid ion is 10% denser than the Earth's outer core. This shows some lighter component should be existing in the core. So, on the basis of geochemical, cosmochemical, and geophysical observations, those candidates are proposed means hydrogen, carbon, sulfur, oxygen, silicon. However, the nature of the light element in the core is still controversial because no available natural rocks from origin from the center of the Earth, and also poor knowledge for these light element effect on the physical properties ion corresponding high pressure conditions. So when we look at the core, more than 90% is a liquid. And also, the fundamental information of the Earth's core is the seismic observations, means the sound wave velocity. So that figure shows the comparison between the seismological observation and the liquid ion. And then 3%, the Earth's outer core is 3% faster than liquid ion is estimated from a shockwave experiment. So, sound wave velocities of liquid ion light element alloys are very fundamental to constrain the composition of the core, because fundamental sound velocity data we can compare directly. And then also the liquid outer core is more than 90%, not solid. So we decided to challenge the sound velocity measurement for liquid iron carbide and iron sulfide samples using diamond ambuscell and high energy resolution inelastic X-ray scattering spectroscopy. Because the last forum meeting, already some of iron sulfide data has been presented. So I will be explaining our experimental procedure with the iron carbide sample. So we use a laser heated diamond cell. We load the iron carbide mixture with the full weight % carbon packed into the diamond cell together with a single crystalline sapphire chemically and thermally insulated. So pressure determined from the lattice parameter of the sample Fe4wt or diamond Raman shift before experiment. So laser spot size was 50 to 70 micrometer. We also use external heated diamond cell in some experiment performed at a relatively low pressure below 20 GPa. This external heating diamond cell is very simple. Just the diamond is surrounded by the metal wire heater. So temperature gradient is very homogeneous in this cell. And temperature is measured with the platinum rhodium thermocouple. And both diamond ambuscell cell packed in the vacuum because air scattering causes lots of background for inelastic X-ray scattering measurement. So we use highly monochromatic X-ray and focused on the sample from right side, and diffracted X-ray was detected by the XRD detector, also scattered inelastic X-ray detected by the high resolution spectroscopy. So we used silicon 999 configuration that gives the 3.0 millielectron volt energy resolution. So first I show the XRD diffraction, and both figures show the diffraction patterns. Left one is one dimensional, and the right one is two-dimensional. So you can see the ion and the Fe4wt C, our sample, together with the insulator material aluminum peaks. If it goes to the higher temperature at 31 GPa here and at 2160 Kelvin, we cannot see any sample peaks, only the sapphire, the insulator peaks. And if carefully look at the diffraction pattern on the left side, the red one, and you can see there's some diffuse scattering. So we judged merit from the sample peaks disappearance and sometime, not always, but appearance of diffuse scattering. So after check the melting of the sample, we collected IXS spectra. In our beam line, we can collect IXS spectra at 12 independent momentum transfer simultaneously. And we collected data in the energy range from 40 to minus 30 or minus 10 millieV, and this takes us to around the 1 to the 2.5 hours. This is typical IXS spectra. So this spectra consists of three components. One is zero energy shift central peak from quasi-elastic peak, and two acoustic phonon excitation modes from sample liquid iron carbide and also diamonds. So for acoustic phonon modes, you can see a double, but in the positive Stokes side, in the negative anti-Stokes side with the same energy. After fitting, we plot the excitation energy for the sample as a function of momentum transfer. So our target P wave velocity is long wave velocity, means the gradient of the excitation energy over momentum transfer at Q0 limit. So to determine the P wave velocity, we fit a linear curve for only low Q data below the 3.5 inverse nanometer, because higher Q range, sometimes unexpected dispersion curvature were observed. So we determined the sound velocity from 7.6 to 68 GPa, and that in the temperature range 1480 to 2800 Kelvin. So red symbol is determined the sound velocity for liquid iron carbide and plotted as a function of pressure. So the line is fitting curve with a very simple equation on the basis of Mannerheim equation, and also without any temperature effect on the sound velocity. The red are sample velocity compared with the solid data observed by the similar IXS method for solid iron and solid Fe4wt C. As you can see, apparently our sound velocity is much faster, roughly 20% faster than the solid phases. Considering any temperature effect on the sound velocities, this difference is a very good signal for we successfully measured the sound velocity of melt sample. We also measured the liquid iron nickel sulfide after 46 GPa. I briefly show the data. Iron sulfide velocity data is blue one, and compare with recent ultrasonic data for the similar composition. Some gradient or pressure effect is a little bit different between our IXS data and the ultrasonic data, means our IXS data shows more gentle. But this difference may be some structural changes in the iron sulfur liquid is reported by the previous study at around 20 GPa. So together, iron carbide liquid data and iron sulfide data, we compared with pure iron. So red is carbide data, and blue is sulfide data. And apparently, compared with the liquid pure ion data, both elements makes ion become faster. And to more apparently, I would like to show the effect. In this diagram, I plot the difference of the sound velocity of carbide and the sulfide to the pure ion in the percentage, but plotted as a function of atomic percent. So solid and the broken line shows at 70 GPa difference over 4 carbon data relative to ion, and 20 GPa difference and 70 GPa, but for sulfur, 20 GPa for sulfide. So in this plot, for example, at the given 15% carbon over sulfur, carbon more enhance or significantly increase velocity over liquid ion. And also, in addition, I would like to mention about the increasing pressure, the sound velocity may increase a little bit for both elements. And if I'm allowed to compare with this data to the outer core velocity data, but at the core mantle boundary pressure, 135 GPa. So the outer core is around 3%, is faster than pure ion to the 0%. But our carbon data, even there 2.5 mole percent corresponding to the 7,000 ppm of carbon, explains that this are faster velocity of the outer core. For sulfur, is from 5 to 8% is enough to explain the sound velocities of the outer core. But this amount means 7 to the 1.4% for carbon or 5 to 8% for sulfur. It sounds a little bit low if we would try to explain the core density deficit. I mean, 10% core density deficit. So it is not unclear the trade-off among the lighter elements, the effect on the sound velocity. But I simply conclude from our experimental data, carbon should not be the dominant in the outer core because only the few percent, 1% carbon already explains the velocity. More carbon cannot explain the sound velocity for the Earth's outer core. And sulfur is still questionable. Reasonable amount can be was determined, but I recommend we should be considered with other possible light elements, for example, the silicon, oxygen, and hydrogen. Thank you very much for your attention.
Yes?
Can you remind everyone why Vp increases with the content of light element? Is just mass or is it something else? Why? Why is Vp increasing?
With the light element. Because okay, my understanding is put the carbon or sulfur. I mean, some impurity push into the ion, maybe makes liquid ion structure much harder, not softer.